Hello, welcome back. Today we're going to talk a little bit about torque. So we have seen the rotational counterparts for displacement, velocity, and acceleration. The question is there a rotational counterpart for force? Answer, yes. Long answer, sort of. So forces can act on a rotating object to move it in a linear way. Forces can also act on an object to cause rotation. To make an object start rotating, a force is needed. The position and direction of the force matter as well. The perpendicular distance from the axis of rotation to the line along which the force acts is called the lever arm. A longer lever arm is very helpful in actually rotating objects. So if we look at this door, which would be easier? Would it be easier if you are right here, pushing close to where the hinge is, or if you push way out here with a very long lever arm where the knob is? Obviously, if you push near the knob, it's going to be a bit easier to open the door. So if I were to give you two choices on picking up the same massive object, where would you rather put your pivot point? Would you rather stand on this side over here, pulling down on this bar to lift this mass over here, or would you rather have your pivot point way down here next to the mass, giving you a very long lever arm? Hopefully you want the long lever arm, and in one of our problems you'll see why. So torque. The units of torque are a Newton meter because it's a force, a Newton, times a distance, meter. It's not to be confused with the joule, which is also, when broken down, a Newton times a meter. I don't make the rules. Sorry. So geometrically, you have two options which mean the exact same thing. First, you could multiply the portion of the lever arm that is perpendicular to the force by the force. So this portion of the lever arm is perpendicular to the force, and that would be this equation, this part right here. Or the second choice is break your force down into components. So you have a force that is perpendicular to the lever arm, and that is this equation. They mean the same thing. Sometimes it's easier to use one rather than the other. That's pretty much it for torque. Let's hit a couple of problems. So first problem here. Calculate the net torque about the axle of the wheel shown in this figure. Assume that a friction torque of 0.4 Newton meters opposes the motion. Well, torque problems come in two flavors. They're either circular, like you're seeing now, where the problem, it's the radius of the circle is the moment arm. So in this case, your 12 centimeters here would be the moment arm of this torque. The 24 centimeters would be the moment arm of this torque and also this torque. The other type of flavor is linear, where the distance between the force and the fulcrum is like the same moment arm. So for this problem, we do have three forces. All of them are conveniently tangential to the circle, which makes them perpendicular to the radius, which is their lever arm. In other words, we actually have squares here. So torque is just force times the moment arm. When we have three torques, in order to get the net force, in order to get the net torque, we just add them up. In this case, the 28 Newton force being counterclockwise is a positive torque, and the other two being in the clockwise direction are negative torques. And torque, just the force perpendicular, multiplied by the lever arm, the radius. So we get a total torque in this case of negative 1.8 Newton meters. And we can translate that, of course, into 1.4 Newton meters clockwise. One more problem. So what is the minimum magnitude of force required to push down at 2 meters from a fulcrum on one side of the lever to lift a 500 kilogram object that is 0.1 meters from the fulcrum on the opposite side of the lever? So this is an example of a linear torque problem. And we solve it basically the same way. The problem calls for the minimum magnitude required. That should be right at a net torque equal to 0, or actually just an infinitesimally small amount above 0. So we're just going to call the torque 0 and then do a sum of torques equal to that. So the sum of torques in this case would be the sum from our left-hand side minus the sum from the right-hand side. Now we'll notice minus. Minus is because this torque is actually going to end up rotating the object in a clockwise direction. So we sum that all together and we get a force required of 245 newtons, or roughly the mass of a small child sitting at the 2 meter point, lifting up a 500 kilogram whatever engine of a car, a very heavy engine of a car. So as always, thank you for watching this video, and please remember to check as you learn for the remainder of your assignment.